We would like, for the next 40 minutes, we would like to get you through the large-scale log analysis with Solr by me and a colleague of mine. And actually, there was a talk about time series-based data earlier today. So if you haven't watched it, or we encourage you to do so after the conference, once the videos will be published, this talk will be complementary to what we actually will say about it. So allow us to introduce ourselves a bit. I'm Rafał. I work for a company called Sematext. We provide log analysis solution, performance monitoring. I'm a consultant, software engineer, trainee. I wrote a few books around Solr and Elasticsearch, and I happen to be a father of 2 great kids. And this is my colleague.
I'm Radu. I'm his colleague. And yeah, I do pretty much the same things as he does. So yeah.
Yeah. So the agenda for the next 38 minutes is to show you both the ways of how how we can analyze logs with Solr and the performance metrics around that. Because not all tools have the same performance, the same memory usage, etc. We'll start with Logstash and how to configure it and push data to Solr. We'll show you the performance metrics around that, and we'll show you different type of processing there. We'll also tell you and show you how to do the same with our Syslog, almost the same, and then introduce you to a larger pipeline, more complicated, though more flexible, using a centralized queue. In the talk, we've used Redis. You can use Kafka, for example, as well. After the shippers part is done, we'll tell a few words about Solr scaling in case of time series data and log analysis, especially for the use case we've done here. So allow me to start with Logstash. If you've known Logstash, by the way, how many of you use Logstash? Okay, quite a few. Nice. So Logstash, for the rest of you, Logstash is divided into 3 main parts. The first part is the inputs, and it's quite modular, of course, because of that. The first part are the inputs, which read your data from various sources. We can have a raw Apache log consumed by Logstash, tailed actually, and we'll read the data. We can have it consumed from Redis, Kafka, or anything actually we want, and if the plugin is available. And this is those are called inputs. There are codecs that allow us to transform the data that we read from the inputs, like the plain codec, which we will use for consuming from Apache, because it will read just data that doesn't need to be cut into pieces of a single line. And for Redis, we'll use the codec JSON, because we will have the data in JSON already pushed that. But that's something that will come later. Then we have the second part, which are the filters. The filters are the part that give the data that we read from the inputs a structure. Like here, we see an example of a logline like Rafał and my Twitter handle. We use a Grog filter, which I'll get back to in a future. It basically allows us to use regular expressions to parse data. And it would result, after passing it through Grog, it would result in a structured JSON document that has 2 fields, user and Twitter. And that's how filters are processing the logs. Of course, Grog is not the only filter that is available. We can use multiple ones like GeoIP that will provide us with the latitude and longitude for the IP address. Of course, we can define the number of workers, which are basically the number of threads used by filtering. Finally, after we have the data processed, we can use an output to push the data further. Like in this example, we use that output that Radu made to push the data to Solr. We, again, can configure the number of workers, which, again, is basically the number of threads that will be used to push the data. So getting that into working, we started with the example Apache log that was unstructured, unstructured, basically a text file that each line contains a log. By the way, you don't have to note anything. All the examples are available on our GitHub account, so you can just clone it and you'll have all of that we've used. So as I said, we need to configure 3 things: input, filter, and output. In that case, filter can be omitted, but we need to specify the input. In this case, we specify the file input, which tells Logstash to get the data from a file. We specify the path, and the start positions start from the beginning and tail the file. The output is a Solr HTTP module that needs to be installed because it doesn't come with Logstash out of the box, but it's as easy as running the bin plugin install command and providing the name you can see on the slide. Again, configuration is very, very simple. We just provide the Solr location. By using the Solr URL parameter, we provide the host, port, and of course the collection name. The flash size is the size of a bulk of a single message, and the workers are the number of threads that will be used to send the data. With that configuration, we've got those base results. Those were done on a machine with 4 virtual CPUs, and we've got Logstash to consume about 260% of CPU, which means more or less 2.5 CPUs. Let's take it from there. It used 350 megabytes and was able to process about 3.7K messages per second. So 3,700 logs per second were processed and sent to Solr that way. Not bad. But we also wanted to test how it would look like if we would just use the structured data already, like a JSON one. So we configured Apache to throw data into JSON. And we've used the JSON example and a filter because we wanted to actually test multiple threads filtering at the same time. We can't do that with codec. We can do that with a filter. So we defined the JSON filter, and we've run Logstash with, OK, it's not that visible, with -W4, which means 4 worker threads for filtering. And in that case, we've got something like the same CPU, slightly more memory usage because the logs are now structured, and the JSON is a bit more weightier when it comes to the comparing to the pure raw log. But look at the events per second. It dropped more than a half, from 3,700 to 1,600. But you also would like to do something with the logs, actually. You would like to search them, analyze them, and we can't do that till now because we put a single message. So now we introduce a filter that uses a filter called Grog. It's a simple filter that actually hides the regular expressions from us. By using a single dictionary input like the combined Apache log, we tell Logstash to actually take a few regular expressions and and parse exactly the Apache access log with it. It's a way of not using regular expressions while you are actually using them. But for example, like me, you're afraid of regular expressions. So I find Grog very, very nice. And using Grog, of course, we increased the usage of the CPU to almost 3 virtual cores and slightly more memory. That's actually something to be expected because we are using regular expressions to parse the data. But still, we had the same events per second. So that means that the Grog is quite nicely optimized because it needs to parse each message. And so how the flow look like when it comes to Logstash being used and directly pushing to Solr? So we have a Logstash running on each of the servers and pushing data, tailing the data, pushing the data to Solr. And that's not something that you may actually want to have in production. Because on the servers, especially the ones that are utilized well, you would like to have more CPU cycles and memory for the stuff you run there, like Solrs, for example, or database or anything like that. So Logstash taking the CPU and memory is not the best idea. That's why we can, for example, include our Syslog there and push data from there, or push data to a centralized queue. And when it comes to our Syslog,
hello, I'm the fanboy of our Syslog. So you're probably familiar with it, like it's the default Syslog daemon on many distributions. So just to run through how it kind of works behind the scenes, you can have multiple inputs. It's also modular, so you have inputs, message modifiers, and outputs. So you can tail files, for example. You can read from the syslog socket, obviously. You can get kernel logs and so on. So those will be the inputs. And the inputs, the threads that run the inputs will push messages to main queue. You can also have more flows like this by using rule sets, but in this case, we'll just use just one main queue. And this main queue can be configured to store events in memory, on disk, or a combination of both, like writing to memory up till one point and then splitting to disk. And on this main queue, you have a configurable number of threads that can do like the bulk of your work, basically doing filtering or parsing or even sending events, because and it does that in batches, so you can configure how big these batches would be. And then the point would be to perform some actions. Actions could be parse the unstructured data and make it structured, or forward this stuff over the network, or write it to a file. In this case, we don't have an output module specifically for Solr, like natively, but we have an output module that can pipe to an external program. So if you use this, each worker thread will spawn its own process and then like take care of it. So if it dies, it will respawn it. And we want to push our documents structure, so let's say JSON, into Solr. So to make the work easier for the external application, it would be nice to make our Syslog output JSON. So you can do that by using templates. And a template is a way of telling
Sorry, Radu. By telling Solr.
Not by telling our Syslog to take the variables that it parsed and like build a string out of that, and that string could be a JSON. And then the external app would just push those JSONs to Solr. This is how a config would look like. Again, don't have to write any of this huge stuff down. It's all in GitHub. The point is you would first load the modules, like the one that tails files, the one that can write to the external app, and then, actually define which file you want to tail. And then there's the main queue configuration, like how big would it be. In this case, it's one of those disk-assisted configurations. So it writes until the high watermark is reached in memory, and then it goes to disk, to that file, up to 5 gigabytes. And we use 4 worker threads to process 500 messages at once. And with that off, we would just build the template of this is how, this is the properties that you want to include, like timestamp, message, and so on. And you can configure that, obviously, and build the JSON out of it. And finally, you have the action of sending to an external app. And you can get that thing that can write to Solr. You can get it from our Syslog's GitHub. And now let's look at performance. So with this sort of simple config of just tailing and pushing stuff, we get 8,000 events per second, 20% CPU, and 170 megabytes of RAM. And this is actually broken down between our Syslog and the little Python scripts. So it's 15% used by our Syslog and 1% for each of the Python scripts. And the same with memory. Each Python script took about 15 megabytes of memory. And the 125 in our Syslog actually depends on how big the queue is. In this case, 100,000 events went to memory. So obviously, if I had a bigger memory queue, it would take longer. It will take more, and so on. But you typically want your logs structured in Solr. So the easiest way to do that, like Rafał did earlier with Logstash, is if you can have your logs already in JSON, like make Apache write JSON. And then you can tail that. You can verify if it's actually a valid JSON by using the Normalize module, which is somewhat similar to Grog in the sense that you define some rules to parse data. And in the case of JSON logs, that rule will be very simple. You will just say, parse a JSON, and if it's valid, you will put it in the root variable. And then the template will be very simple because you don't have to handpick properties. You'll just say, root contains my JSON, so that's my template. And the performance of this is obviously worse than just taking stuff and dumping into Solr. We have 4,500 events per second, 70% CPU, more memory used at 330 megabytes. You can also use Normalize to parse unstructured data and make it structured, again, like Rafał did with Grog. And this is, you can have two kinds of rules. These are like the more verbose ones. You basically have some specialized parsers, like to parse a word or a number or a float or whatever, and you would write these rules and put the parse stuff in its own field. And a rule like this, for example, can parse like the Apache combined log format, and then if the parsing is successful, all the fields go into this predefined old JSON variable. So again, we can use that as a template. And the performance of this is obviously worse than with just parsing JSON. We get 160% CPU, less memory, just 225 megabytes of memory, and 4,000 events per second. And this is the interesting bit, like why does it use less memory? It's because of the way normalizing works. As I said, we have these specialized parsers, and you can have multiple rules, obviously, to parse multiple types of logs. And then our Syslog, when it starts, it builds a parsing tree. So this dummy example will parse system, syslog-d, and syslog-ng. And the point is, because it goes character by character through the whole log, the performance doesn't depend on the number of rules. It depends on the length of the log. And also, the memory usage depends on the length of the log. And JSON logs will be bigger than the unstructured logs, and so that's why it used less memory. And we actually put this claim to the test that it actually scales nicely with multiple rules. So we parsed multiple flavors of Apache logs, combined, common, or just JSON, or the timestamp and the blob of data, and so on. And the performance was very interesting in the sense that we got lower throughput, but we also got a lot lower CPU. So in terms of efficiency, it was actually better with 5 rules than with just 1 rule. And this is because some of the logs were a bit smaller. So I think in the end, it kind of evens out. But the memory usage increased. So yeah, the more rules you have, the more memory this will take. So we showed how to push directly from our Syslog to Solr. But we also wanted to show how to push to a central queue and then have Logstash pick things up and maybe do some more of its magic before pushing to Solr. So how this will look like in our Syslog is, instead of pushing to an external program, you would use the Redis output module, and then it'll be the same input, obviously, and probably in such a use case, you want our Syslog to be as light as possible, so you can limit it, for example, just to work on 1 thread and have a small in-memory queue. And then you will have the configuration of the Redis module where we will specify the key where to publish the stuff.
So in that case, where we have the data already structured by our Syslog and pushed into Redis, we may want Logstash to actually read from there and push directly to Solr. In that case, we don't need to change the output. It stays the same, but we need to change the input. We just specify Redis input, which is available by default in our Syslog. JSON codec is used, so we don't need any filtering. We specify the data type as a channel, the key the same, which we've used in our Syslog configuration, and the batch count, which just means how many documents fetch in a single request. Of course, our Syslog, for example, don't have GeoIP filtering, so we could enrich data in that step where actually our Logstash reads from and sends to Solr. But we don't show that, and we want to concentrate on performance.
Yeah, so with this kind of approach, it's a bit weird to measure performance because in all these tests, we just used a single machine. So Solr was there, everything was there. And what we actually show on these counters is the ingestion pipeline. What's the overhead of it? And in this particular case, like our Syslog starts up and it tails the file and pushes stuff to Redis as fast as possible. So it goes to 100% because it has only one thread. But it gets rid of the data very quickly. It pushes, in this case, it was something like 250,000 events per second to Redis. And in that time frame, our Syslog was using one CPU, and then it didn't use anything. And then Redis, on the other hand, used like 25% CPU, and then it didn't use almost anything. So we just like made an average and said our Syslog will use 1% of CPU through the whole time Logstash takes to push the whole data set, which was 3 million documents, to Solr. And Logstash, in all this time, takes about 200% of CPU, 200% of CPU, 2 CPUs out of 4.
Yeah.
And the memory usage, again, you have to sort of break it down. Our Syslog, because it has a tiny queue, it uses very little memory. Redis uses a lot of memory because it buffers all the 3 million logs, and Logstash uses the same memory as before. Sure.
So what is the gating factor here? Is it pushing to Solr? Is that because Logstash is taking more time? Let's say Logstash or writing to file system or memory, would it take same amount of CPU?
I'm not sure if I got the question really.
Why is Logstash taking so much time? What is holding it?
Yeah, Solr does the most of work because it has to index stuff. So, and also Logstash takes quite a lot of CPU. So, it's Logstash that's being slow and Solr that's being slow. So the other stuff, just picking from a file and shoving it into Redis, which is just a memory storage in this case, is very fast, and the other stuff is slower. Like Logstash has to parse the JSON on the input, and then push it to Solr, wait for the reply. And then Solr obviously has to do a lot of work, so that's why things don't go constantly.
Okay, go.
And we also tried to do normalizing, actually with those 5 rows that we've shown earlier. And because we have a lot more data, because we have 5 files of 3 million each, our Syslog stays longer at 100%. But the rest is pretty much the same, and obviously because our Syslog takes one of the 4 CPUs, we have 1/4 less throughput. So that's pretty much it.
Actually, we've shown you 3 setups when it comes to log shippers. The first one is very easy to set up, very flexible because we are using regular expressions to parse the data. But it's quite heavy when it comes to resources because you've seen the metrics, and because of that, if you need something fast to take your data and push it, that setup can be an option. But in general, you would like more something like the second one in the middle, which is light, fast, but compared to Logstash, it's less flexible because it by default doesn't use the regular expressions, but those tiny parsers that Radu mentioned, but it's less easy to configure. You remember the configuration files that Radu shown that took 2 slides instead of only those tiny pieces. This is the
very small font.
Okay, this is the downside. Of course, you can combine those 2 approaches and do the third setup, which is more flexible, offloads processing, but the problem is the maintenance overhead because you have all those moving pieces around. So you have the centralized queue, you have our Syslog on each of the machines, and you have Logstash. Of course, that allows you to process and enrich the data. You could actually remove the centralized queue and push directly from our Syslog to Logstash, but then you would have to rely on our Syslog queues to be in use. So we've now won't talk more about the shipping. Now, of course, the final part of that ingestion pipeline for the logs is Solr. And when it comes to Solr, we would like to mention 3 things. First of all, tuning the one instance of Solr, which goes to schema and config adjustments. Of course, we can use time-based collections and tiered clusters, especially for the logs and the data that is time-based. You can imagine that for logs, we have 2 kinds of fields that we are actually interested in. Of course, they could be analyzed differently, but in general, we have the fields that we want to use for analysis, like faceting, sorting, and we have the fields that we would like to use for searching. The fields that we would like to use for analysis should use doc values that will save us a bit of memory at the cost of slower indexing, slightly slower indexing. For searching, we for sure omit norms because we don't use scoring most of the time, because when we search, we sort using timestamps. So we just sort based on time. And we could, if we don't want to use phrase searches, which is not always the case, we could omit the norms, we could omit the frequencies as positions of terms. So this is again. And having all of that, we could end up with 10% faster indexing for the whole collection and 20 to 100% more capacity, which is actually what Radu talked about last year with the link below. The capacity depends really on, is what we call when you can handle the same amount of queries with more and more data. So this is what we could end up with. When it comes to the configuration of Solr itself with Solr config, we of course could set up how often we refresh the index view. 5 seconds for the logging use case is usually more than enough. We can go below that, like to 20 seconds to 30 seconds, not more, because it doesn't pay off really after that. And of course, we would like to flash the data to disk not as often as it gets to Solr, but with some buffering. So flashing every 1 minute or 200 megabytes seems to be a good trade-off when it comes to consistency. And with that approach, we again got to 10% of capacity and 10% faster indexing. So with the same hardware, we can actually have more logs and process them faster.
Okay.
We can also use time-based collections.
Yeah, so basically if you hold your logs for a week, you can have, for example, 1 collection per day. And this is good in like all across the board, because when you're indexing, you're going to be indexing into a smaller chunk of your data, so you're not going to merge as much as if you would do if you had a single index. Then when you search, most searches will run probably on recent data, so again, you're going to isolate that. The indices that are, the collections that are no longer updated, will remain the same. They're more cache friendly. You can even optimize them, though that is kind of debatable if it helps. And finally, when you expire data, instead of deleting from the same collection and causing more merges, you can expire entire collections. And this is actually the thing that got us the most sort of improvement in terms of capacity. Both in last year's test and earlier this year with Solr 5.2, we got somewhere between 20 and 30 times more capacity by using this design than by using a single collection.
But that's not all. You could also divide the cluster into 2 pieces, the one called hot and the one called cold. How that sounds, okay. The reason for that is that only certain nodes could do indexing and certain nodes could work as an archive. So the hot nodes would be the ones that work as indexing horses and index the data, while the other ones would be used only for the archive of the data and searches in the longer period of time. How that would work? First, when we create a collection, we would create them on the hot nodes. Then we index data for the whole day. Let's assume that we have daily collections. And we index data for the whole day. And once the data is indexed and we switch to a next collection, we would just use the collection API to add a replica on the cold nodes and remove the leaders from the hot nodes. And we would have the data on cold nodes. Of course, at the same time, we would create the collection for the next day, and the data would be indexed by a shipper to a new collection. For example, Logstash handles that easily by just having a properly named collection, and it will just switch automatically to a new one. And this, again, if the day ends, we would just move the collection to a cold nodes further, and we have another new collection created on the hot nodes. In that way, we divide the cluster into 2 pieces. The quick and recent searches and indexing is done on the hot nodes only, while the rare lengthy searches when you need to search for the historical data is done on the cold nodes. Of course, on the hot nodes as well, but most of this search will be on the cold nodes because the data is there. In such case, we can scale actually independently those 2 pieces because we can add more hot nodes if we need more indexing power. Then we will just create more shards for the collection, put it on the hot nodes if we have more nodes, and we will have more processing power for indexing. For the cold nodes, again, we can do the same. If we would like to extend our monthly period of data to something like a year, we would just add new cold nodes and add replicas, move the data, and keep it like this. This is something that you don't have to actually over-provision the whole environment, just pieces you actually need. So that, again, can save you money when it comes to the hardware. When it comes to the resources needed, in most cases, the bottleneck for the hot nodes will be the CPU power. And you need, because of the merges and all the indexing happen, when the merges happen, CPU is used extremely, so that's needed. Of course, some degree of I/O performance will be needed as well, because if you ingest large portion of data, like the logs one, and they constantly flow, you will need that. In terms of cold nodes, the most precious resources and the ones that will cause bottlenecks are the memory, because of the amount of data you will have there, and the I/O, because not all data will fit into the operating system cache, and you'll need the I/O to just read the data. Of course, you won't expect the same amount of performance from the cold and hot nodes, but this is optimization to save you the costs. And actually,
yeah, that's pretty much it. Let me sort of wrap this up. So hot and cold nodes, that might be a good idea to sort of isolate things, and you can do that if you use time-based collections or time-based shards, as was shown earlier this morning. In terms of configurations, tuning your commits will probably improve your indexing throughput, and using doc values, the capacity. In terms of indexing, if you want something easy to set up and flexible, you can push from Logstash directly to Solr. If you want something really fast, you can try use our Syslog. If you want something from both, you can like couple them either directly or through a queue like Redis or Kafka or, I don't know, ZeroMQ, whatever is supported by both. That's pretty much it. If you have any questions, I believe we have 5 minutes left. Yeah.
So I have 2 questions. The first one is on, do you have any recommendations? So from the, just before you're about to post to Solr, right? What should be the batch size? Because I think the other aspect is to also keep the CPU on the hot cluster at around the maximum, right?
I thought about a minimum.
Basically for ingestion, if you want to do maximum.
Oh, like just through, most throughput, okay.
From your Logstash onto that thing, right? So generally your batch size of how many documents you're throwing in one post to Solr also matters, right?
Yes.
Figure out something like how much that batch.
Well, I think
5,000?
we used 5,000
yes,
for this test.
yeah, something like 5,000 during tests, and it was most optimal. We've got the best throughput with about 5,000 documents in a bulk, but that also depends on the.
One document, 1 KB, something like document?
More like 250 bytes or something like that.
Yes.
Yeah,
and the
like
test
a regular Apache log. I'm not sure how.
Another question is on the doc values. You said that it has an impact on the capacity, but you didn't mention how much slower it makes the ingestion.
Oh, well, with injection, we didn't feel anything, to be honest. I mean, just by the change, we didn't see any slower ingestion.
It's in theory it will be slightly. It will because you need to write that uninverted data to an index actually. But with tests we haven't had any changes. It was like a statistical error during the test, so nothing to include in the slides. Maybe with the larger amount of data that is only pushed to Solr without Logstash eating the CPU and memory, we would see the difference compared, but we use Logstash on the same machine.
When I tested that last year, it was only Solr and we're big machines, and we had, I don't know how much indexing throughput. It's just because a lot of the CPU is taken by merging and actually indexing. So. And I/O is only, if I/O is the bottleneck, then you have a big problem. Like normally when you're indexing, I/O is going to be fine. Sorry?
Any recommendations on the merge factor? I think it's like you guys did deep.
Yes, actually merge factor, leave it default. Yeah, like I've tried to tune, and like this is something to tune, like because if you have a small merge factor, then your queries should be faster, but then caches are invalidated more, so you're not gonna get faster queries. And then if you have a higher merge factor, then yeah, you might want to change the maximum segment size. That's why you made that face. Yeah.
I was
Because
about to say
you may
that.
want to avoid, you may want to avoid like merging really big segments, because that will eat I/O and CPU, which is precious, especially on the hot nodes. Sorry?
Reduce the max segment.
Reduce the max segment size. That might help.
Yes.
But the merge factor, yeah, don't. I mean, you can test. Maybe it's different for you, but every time I'll fiddle with it.
That you guys did were pretty awesome in terms of looking at the very low level things. So I was thinking, because those are the next factors you have to attack, right?
Yeah, sure.
And it actually works. We use it as well. So this is not something artificial just from production use and experience. So it does work.
More questions?
Since the lexing in our Syslog was considerably faster, did you explore any other opportunities like Yak or Antler to do lexing than Logstash, because that's regex and that's automata is very slow?
But can you tell me how these are? Because I want to look them up. Like what?
Yak,
Yak.
Yak or Antler.
Okay. So these are like parsing frameworks? Or?
If your grammar is known,
Mm-hmm.
use the lexer.
Okay, something to play with,
Because
I suppose.
Logstash, because we're already using our Syslog's grammar to split to lex.
Yes.
Which means very low CPU as you prove.
Yes.
And Logstash is regular expressions, and automata is very, very expensive.
Yes.
So that's to backtrace,
Yes.
depends on your
Yeah,
regular
exactly.
And then your Yak parsers, you can throw away Logstash altogether and just put it actually in the update processor itself. Solr.
Yeah, true. The thing is that sometimes you want to use Logstash for enriching the data, like for adding the GeoIP filter and turning your IPs into latitude and longitude. For example, do a heat map.
You can do that in our Syslog with me.
Yeah, you can
You
do.
have repeaters anyway, right?
You can do that, but the thing with Logstash is, if it often happens that you're in a hurry, right? You don't.
Yeah.
Nobody wants to stay like to have you debug things for a month to get your indexing pipeline. So with Logstash, my experience is once you know your way around, it's like half a day to do pretty much anything.
But then 2 months to debug performance.
But at least you have like a minimum viable product, and then you can use these 2 months to do.
And then you can switch to our Syslog. Yeah. Okay. If you have any more questions, we'll be here. We'll be at the booth. So once again, thank you for coming. Thank you for listening, and enjoy the rest of the conference.